Moving on to sequential consistency, let's briefly remind the key ideas of it. First, there is total order of all writes. In that total order, operations from the same process, they follow its sequential steps in the same process. So if process A executed operation 1 and then operation 2, then in our total order of operations, these operations 1 and 2 from process A, they will be in exactly the same order. But if we speak about operations between different processes, and we have process A and process B, and the operations of those two different processes, they are not ordered. So we have some order because we require total order, but it's kind of some other order which is not related to recency. So we, for example, could have in real time first process A executed some operation and then process B executed some operation. And in real time they are clearly ordered. But in sequentially consistent total order, they may appear in different order and it will be okay for sequential consistency. Unlike linear reusability, which requires this total order to follow recency of all operations. To see more examples and more explanation on sequential consistency, you can check my separate video about Introduction to Consistency Models. I explain those concepts very understandable and easily. And it seems that with a traditional leader-follower system, where we have only one leader and multiple followers, we can't really get sequential consistency. Because if we use it with a strict configuration, we will get linear reusability. And if we try to use some weaker configurations, then we get only some weaker consistency models, as we described previously, like eventual consistency, consistent prefix reads, session guarantees, or causal consistency. But if we consider a special case when we have single leader system but with multiple shards, where each shard has its own leader, then we can get sequential consistency. But first, let's start with just illustration why we can't get sequential consistency, pure sequential consistency, in just traditional single leader system without partitions. Because in leader-follower systems we could have synchronous or asynchronous followers. Let's review them one by one, and let's start with asynchronous follower. And here let's just show one simple illustration of broken sequential consistency with asynchronous follower. So assume client assigns 1 to X, writes it to the leader and gets acknowledgement. Because of the asynchronous follower, it has some replication lag before replicating it to follower, and only at this point in time this write reaches follower. But client could read after it made the write and it gets 0. This example violates sequential consistency because in sequential consistency all operations of one process or one client, they should be ordered properly. And if client writes 1, then it expects to get 1 as well. So this example violates sequential consistency. But let's try, for example, to add the requirement of read your writes and see if leader-follower system with read your writes requirement would provide a sequential consistency or not. In that case, this example would satisfy sequential specification, but let's see more tricky example when it would not help us. An example here illustrates the scenario when we have 2 clients, 2 followers, and a leader. And assume client A wrote 1 to X on the leader, then client B wrote 1 to Y on leader, then client A makes the read X and client B makes a read of Y. And assume that those reads went to the leader because we now say that our system provides read your rights guarantee, and if those rights are not yet propagated, then the only way to achieve read your rights is to read from leader. And then each client will read the value which were written by the other client. So client A would read Y and will get 0 because by default it would read it from follower, because the only guarantee that we imposed it's reading your right, and reading your right is satisfied, and Y was written by other clients, so it does not have to do anything in the common with our guarantee of reading your rights. So basically it reads 0, and the client B reads X from follower and also gets 0. And this sequence contradicts sequential consistency. Let's see why. Let's depict our writes and reads, all operations of each client separately. Client A view on the operations and client B view on the operations. And the writes are depicted with orange and red, while reads are depicted with blue and green. So what happens from client A point of view? Client A wrote X here, it wrote 1 to X. Then it made 2 reads. It read X and it read Y and got 1 and 0. And client B wrote 1 to Y and made 2 reads. On the first read it got Y equals 1, and on the next read it got X equals 0. So if we look at the view of each client separately, then it looks to be okay. So basically we written something, we got it back, and then we make some read and got some value back. So each client, it would not see any specific problem. But remember that in sequential consistency we say that we have total order of all the operations of all clients. So let's try to build the total order of those two views. And first, let's just try to arrange them that way. So we have 2 writes, write by client A, write by client B, so just basically those ones. And then reads, read X by client A and read Y by client B, and then reads of the opposite variables. And we see in the total order there are violations of legality of the history. Let's look deeper at them. So first violation is here we read 1 from X, but then we read 0 from X, but between those reads there were no any writes. So basically without any writes, in the total order the state of variable changed from 1 to 0. And it does not comply with sequential specification of register, which basically says that the value of register can be changed only if we wrote something to that register. And here is also the same violation. 2 reads return different results, even though there were not any writes between them. Remember that in sequential consistency we have flexibility to shift operations of different processes relatively to each other. And let's try to do that and see if we are able to fix that inconsistency. And now basically what we will try to do, we will try first to place in our total order all operations of client A and then all operations of client B, and basically now we get that picture. First operations of client A and operations of client B. And still there is one violation, because client A, it read X equals 1. After that, no one wrote anything to X, and then client B read X equals 0. So there is no way we can reorder those operations to get some specific total order which would satisfy sequential specification of a register. So basically we have shown that with asynchronous followers, even with some session guarantees, it's not possible to achieve sequential consistency. So with asynchronous followers, sequential consistency is not achievable. With synchronous followers, if we prohibit out-of-order writes and delayed visibility, then we will get basically linear readability. And linear readability is a stronger model than sequential consistency. To speak strictly, if we get linear readability, we also kind of get sequential consistency because we have stronger behavior. But we can't get pure sequential consistency with just traditional leader-follower system with just a single leader without partitioning of that system. So now let's see a variation of leader-follower system where we could get sequential consistency. For leader per shard approach, let's refer to my other article on my website, which discusses just basics of leader-follower replication and the key idea of per shard leader, that we have multiple partitions, like partitions 1, 2, and 3. And each partition has its own leader and its own followers. And those partitions, the leaders and followers, they can be distributed over the nodes. So one node can have leader from partition 1 and followers from partitions 2 and 3. And the main idea here is that each partition has a single leader, and each data piece, it belongs to only one partition. And it means that in such systems, conflicts are not possible. And also within each partition, there is total order of writes, but we don't have now guarantees of mutual order of writes between different partitions. For example, if we made some write on partition 1 and made some write on partition 2, those two writes will be considered as concurrent. And basically, it's just what is required in sequential consistency. So this leader per shard approach, it's very well fits sequential consistency definition. We just should remember that even with a single shard, if we use asynchronous followers, then sequential consistency is not possible. So it means to achieve sequential consistency, we need to use synchronous followers with prohibited out-of-order writes and with immediate visibility. But we need to have multiple partitions, and in that case we will get sequential consistency when operations within each partition will be strictly ordered. Operations between different partitions will be concurrent, and still we would be able to imagine some total order of all operations that matches sequential specifications of the data storage. It's just worth noting that sequential consistency is a very strict consistency model. And before relying on the fact that we will get that consistency, you will need to carefully read the documentation to your specific database and see what settings you need to set to get sequential consistency. Now let's see an example where it could be useful for us to have sequential consistency with leader-follower replication in some example of a real system. As an example of such system, we will consider distributed inventory system, and let's briefly give some main requirements for such system. And this is basically a system that stores how many products we have in the warehouse. This system, it should keep track of all products. Then we have a requirement that the amount of products is so huge that we can't place all of them on a single node. Secondly, all users of that warehouse are located in single region, so that we can place the whole system in the single data center. And it's very important to prevent overselling when we sell more than we have in the warehouse. And also there is a requirement that the warehouse must survive node failures. And for the purpose of our example, it doesn't really matter whether such system would use relational or document-based storage. But for the sake of our example, we will use document-oriented database, but it doesn't mean anything. And let's assume that we will have product document, which looks like this. It has the ID, name of the product, some description, and category, and the quantity of that product. And the fact that this requirement that we have huge amount of products and they would not fit to single database, it suggests that we need to use sharding and we need to have some partitions and split our products across multiple partitions. There can be many approaches how to implement this, but here, just for simplicity, we will consider that each product will have category and each category will reside on its own partition. So, for example, here we have category electronics, sports, and toys. And there will be shards 1, 2, and 3, and each shard will contain products of only one category. And let's assume that if we split all huge amount of products into some categories, then each category will be relatively small to fit into the one partition, into the one database. We could use a sequentially consistent system with a single leader split by partitions. Single leader is required to satisfy this requirement for us that it's important to prevent overselling, because each product will belong only to one partition, and it means that each product it will have only one leader node which will linearize all rights. And thus it's not possible to come to a situation when we sold the same product twice and our amount of those products would be negative. Because leader-follower system, it has leader and followers, and there is a failover process in case one node fails. Then we satisfy this requirement that warehouse should survive node failures. And the requirement that all users are located in one region, it says for us that we can use only synchronous followers. Because if we know that the users are located in different regions, we would have to place some followers to some remote regions in order to make reads for those users faster. And we could not make that follower synchronous because of the delay of cross-regional calls. So in our example, just for simplicity, we say that all of them will be synchronous because we know that in case of synchronous followers, sequential consistency is satisfied by default when we have leader per shard approach. I just want to point your attention that in reality, most likely we would not do it that way, because placing all nodes in a single data center is kind of risky, and most likely in real systems there would be some asynchronous followers and users located in different regions. But here we just concentrate on sequential consistency and what systems could benefit from it. So basically in such system with such sharding and such structure, all our requirements from here are satisfied, and we have an example of leader-follower system with sequential consistency, which helps us to build this distributed inventory system, which tracks products and prevents overspending. So up to now, we already see that leader-follower schema is very versatile depending on how exactly we cook it, how we use it. So we can achieve eventual consistency, causal consistency, we could achieve some session guarantees, consistent prefix read, and even sequential consistency. And in the next video, we will cover strongest consistency models such as linearizability or even external consistency or strict serializability. And in order not to miss the notification, just subscribe to my channel. See you!